Hello everyone, my name is Maxim and I'm going to talk about our payment trees protocol, which is a protocol for low collateral payments in payment channel networks. In the following, I will first give a little bit of background information before going into a little bit more detail in the preliminaries and lastly showing to you our construction. This work is about decentralized ledgers as Bitcoin. Such a ledger is basically a data structure that maintains a list of transactions. A transaction could be a simple payment, as for instance, Alice sends 30 coins to Bob. It is operated among a set of mutually distrustful parties through a consensus mechanism. Transactions can only be appended to this ledger, they cannot be reordered or removed. Each transaction that should be added onto the ledger has to go through this consensus mechanism, which is quite expensive, so this has some implications on the scalability of the system as a whole. One approach to mitigate this are so-called off-chain-channels. The idea is that we want to reduce the number of transactions that actually have to be sent to the ledger. And well, they basically work like this. Imagine we have two parties, Alice and Bob. First, they can open a channel by sending a transaction to the ledger that takes both of their coins and locks them away into a shared account. This shared account has a state. In our case, we are interested in payment channels. So the state that is stored is how are the coins within the channel distributed between both parties. Alice and Bob can modify the state without sending any transaction to the ledger. For instance, they could modify the state such that Alice has 2 coins less, but Bob has 2 coins more. This effectively would perform a payment of 2 coins from Alice to Bob. Alice and Bob can repeat the step and perform more payments, potentially arbitrary often. And lastly, they can send one more transaction to the ledger that closes the channel and unlocks the coins, gives them back to both Alice and Bob according to the latest state of the channel itself. Doing this, we can perform an arbitrary amount of payments, but only have a constant number of transactions that are added to the ledger. We can concatenate individual channels into payment channel networks. Imagine a situation as you see on the left. We have again Alice and Bob and a channel shared between them, but additionally we have now a channel also between Bob and Charlie. Now we can use techniques such as hash Timelock contracts, or in short HTLCs, to facilitate payments from Alice to Charlie. This is done by basically replicating the same payment on a path of payment channels from Alice to Charlie. These payments are performed atomically, meaning either all of them will be performed or none of them will be performed. Using HTLCs, we can further improve the scalability of the system as a whole, since we now do not need to create individual channels between each pair of parties that want to perform payments with each other. In simple terms, HTLCs work as follows. Here again we have 3 parties, Alice, Bob, and Charlie, and 2 channels, one between Alice and Bob and one between Bob and Charlie, as before. Now, first, Alice thinks of a secret X. Then Alice and Bob, they modify their channel by extending it with a conditional payment from Alice to Bob, and this payment is performed if Bob can tell Alice her secret X. Next, we do this on the next hop of the path from Alice to Charlie by extending the channel between Bob and Charlie with another conditional payment that now pays 5 coins from Bob to Charlie if Charlie can tell Bob Alice's secret X. Now, after we have set up these conditional payments on each individual channel on a path from Alice to Charlie, Alice tells Charlie her secret X. Since now Charlie knows the secret X, he can forward it to Bob and show him that he can enforce the conditional payment, the payout of the conditional payment to him on the ledger. However, Bob and Charlie then can consolidate the payment within the channel and modify its state such that they remove the conditional payment, but give the coins within the conditional payment to Charlie. However, now Bob knows Alice's secret X and can forward it to Alice afterwards. Alice and Bob can do the same, consolidate the payment within their channel and give Bob those coins. Now, effectively, Alice has 5 coins less, Charlie has 5 coins more, Bob has 5 coins less on one channel, but 5 coins more on the other channel. Effectively, we performed a payment from Alice to Charlie of 5 coins. Now, to avoid that the coins within a conditional payment are locked indefinitely, we introduce timeouts. The duration of a timeout, as you can see above, it depends on the number of hops of the payment path from Alice to Eve in this case, and also on a ledger parameter delta, which specifies what is the maximum amount of time it takes for a transaction to be included in the ledger. Now, for the intermediaries, this represents a cost of opportunity. We use the metric of collateral to compute this cost of opportunity, which is the number of coins that are locked away within the conditional payments multiplied by the time they are locked away. Now, because the lock time is linear in the length of a payment path, this opens the door to denial of service and griefing attacks. So in these cases, parties try to sabotage competing channels by routing payments through them in an intent to lock away their coins within these conditional payments. They try to have them locked away for as long as possible. And well, in the case of HDLCs with current implementation, this could be for up to 2 weeks right now. Paper that have analyzed these type of attacks are, for instance, congestion attacks or the lockdown attack. However, also news blogs have been pointing out or reporting on this type of attack as recently as January 2021. So there is an interest in the research community as well as the users to address this vulnerability. Some existing approaches that try to mitigate this issue are, for one, the Sprites protocol, where the authors present an approach with a constant lock time. However, their approach, it requires smart contracts, so it could not be implemented for Bitcoin. Another protocol that tries to solve this issue is the Atomic Multi-Channel Updates protocol. This protocol is compatible to Bitcoin, and it has a constant lock time. However, in our work, we identified a vulnerability in the approach and present an attack. So this is where our work comes in. What we try to do is present a protocol that performs a payment across a payment channel network. It has low collateral or lock time. It is compatible to Bitcoin, and moreover, it is also secure in the presence of a malicious adversary. Our approach is derived from our previous work, which is the lightweight virtual channels protocol. However, we basically try to optimize it to one-time payments. So in the following, I will be a little bit more technical. Our work is based on the model of unspent transaction outputs, or in short, UTXO. A UTXO is a tuple with 2 entries. On the one side, it contains an amount of coins B, and on the other side, it has a script S. Any party can claim the coins within the UTXO by providing a witness W, such that if it is used as input into the script will evaluate to true. In our work, we simplified this a bit by saying the script specifies a set of parties such that if the witness is contains signatures of all parties within that set, then the script will evaluate to true. In this model, the ledger state is represented by all active UTXO. We can perform a state transition on the ledger by committing a transaction to it. A transaction consists of three components. On the one side, we have a set of inputs. An input contains a reference to a UTXO that has to be present on the ledger, as well as its witness. In our case, the witness is a set of signatures. Then we have a set of outputs, which is, well, a set of newly defined UTXOs. Lastly, a transaction can optionally contain a time lock. It specifies a point in time such that before this point in time, the transaction cannot be processed by the consents mechanism and therefore cannot be added to the ledger. Now, an example how this would look like. So on the left side here, you can see the ledger state. Right now, the ledger contains only one UTXO, U1. And at the current moment, we have time t0. On the right, we see a transaction. This transaction has one input, namely the UTXO on the ledger within the ledger state U1. This input also contains the required witness to spend this UTXO. Moreover, it defines two new UTXOs, U2 and U3. However, its time lock is t0 plus 10, such that if we would try to send it to ledger right now at this moment, which is t0, it would not be processed by the consents protocol and not be added to the ledger. However, if we wait 20 more time units, we can send the transaction to the ledger, and the effect would be that the UTXO U1 would be removed from the ledger state, but the UTXOs U2 and U3 would be added to the ledger state. Now, we can interpret a set of transactions as a directed acyclic graph. We do so by saying the transactions form the nodes of such a graph. Each of the inputs of a transaction specifies an incoming edge of that node, and each of the outputs within a transaction represents an outgoing edge of that node. We can observe the following dependencies relationship. Now, if transaction 2, for whatever reason, cannot be committed to the ledger, this could be, for instance, if one of the UTXO that is referenced within one of the inputs of transaction 2, if this is removed from the ledger state by a different transaction, in that case, transaction 2 will never be able to be added to the ledger. Because of this, the UTXOs within transaction 2's outputs can never be added to the ledger, but those are required for committing transaction 3 to the ledger, such that because transaction 2 cannot be added to the ledger, transaction 3 cannot be added to the ledger. And this transitive, so transaction 4 and 5 now also cannot never be added to the ledger. Now we can make use of this property to construct trees of transactions atomically and modify transaction trees. So first, we can modify a transaction trees as follows. Here, imagine we have again the transaction trees from transactions 1 to 5. Transaction 3 has a time lock of t0 plus delta. Now, if we create an alternative subtree, that one that is, instead of being rooted in transaction 3, it's rooted in transaction 3 prime. So transaction 3 prime spends the same UTXOs from transaction 1 and 2 as transaction 3. However, the time lock of transaction 3 prime is smaller than that of transaction 3 by at least delta. In this case, parties who are aware of transaction 3 prime can enforce that transaction 3 prime is added to ledger and not transaction 3. Effectively, we modified the transaction tree and replaced the red subtree with the green subtree. This technique is utilizing time locks. However, different techniques exist, as for instance used within the Lightning Network or as proposed with L2. We can create a set of transactions atomically. Now, for instance, if we want to create transactions 3 to 5 atomically, what we can do is, first, we create transactions 4 and 5. We add witnesses to these transactions. Only after they are created, we create transaction 3. At the moment at which transaction 3 is created, it can eventually be added to the ledger, such that the inputs for transaction 4 and 5 can eventually be added to the ledger. Respectively, now also transactions 4 and 5 eventually will be added to the ledger. We can extend this to create transactions 1 to 5 atomically. We do this in the following way. We set up transactions 1 and 2 such that both transactions contain reference UTXO that require Bob's signature within their witnesses. Now, Bob can act as intermediary for this construction and enforce that all 5 transactions are constructed atomically. This is done by first having all other parties, in this case Alice and Charlie, provide their signatures to transactions 1 and 2 and send those signatures to Bob. Only when Bob has all the remaining components of the witnesses for transactions 1 and 2 outside of his own signature, only then Bob also provides the signatures to transactions 1 and 2. Meaning, if Bob follows this protocol, he can enforce that transactions 1 and 5 are created atomically. However, what if Bob does not act honestly? In that case, we need to incentivize Bob to behave. We do so by introducing 2 more transactions. These transactions spend the same UTXO as transaction 3, but they have a time lock that is higher than transaction 3 by at least delta, such that they will only be ever relevant only if transaction 3 cannot be added to the ledger. So if Bob is honest and creates transactions 1 and 2 atomically, then also transaction 3 can be sent to the ledger eventually, as well as transactions 4 and 5. The 2 new transactions will never be added to the ledger. Bob can prevent, like this, to be punished. However, if for whatever reason transaction 2 cannot be added to the ledger, maybe Bob only provided his signature to transaction 1, or he colluded with Charlie to remove UTXO U2 from the ledger state. In that case, well, transactions 3 to 5 can never be added to the ledger. But now, because of this, since transaction 3 will not be added to the ledger, the transaction on the top can be committed to the ledger by Alice. This transaction takes away all coins from Bob, takes away Bob's collateral, and gives all those coins to Alice. This has 2 functions. On the one side, Bob is punished, and on the other side, Alice will get her coins refunded, such that she is not at any risk of losing any coins depending whether Bob is malicious or honest. With these techniques, we can now present our construction. Here we have a dashed line. On the left-hand side of the dashed line, we show part of the ledger state. Right now, we show 2 UTXO that are present on that ledger. On the right-hand side, we show 2 transaction trees. One that represents a channel between Alice and Bob, and one that represents a channel between Bob and Charlie. Here in this case, we are not interested into the details of how these channels are constructed, so we just illustrate them with some black boxes. The first step of our construction of a payment of 2 coins is to introduce a split transaction. The split transaction's purpose is to split away 2 coins of the channel such that they can be used for our construction. So the split transaction has 2 UTXOs. One UTXO has the payment amount, 2 coins, These coins are taken from Alice's and Bob's balance respectively, and we introduce a refund transaction that gives these coins back to Alice and Bob respectively. The remainder of the coins will be used to reopen the channel between Alice and Bob and between Bob and Charlie respectively. Next, we introduce a merge transaction that combines both of the individual trees, and it contains two UTXOs. On the one side, it pays out Bob's collateral of 2 coins back to Bob. On the other side, it contains a UTXO that requires Alice's and Charlie's signatures to be spent. Together with a refund transaction that pays out Alice's 2 coins, this represents a temporary one-time payment virtual channel between Alice and Charlie. Similar to our example before, we incentivize Bob to ensure that the correctness of this construction by introducing punish transactions that take away Bob's collateral and give it to Alice or Charlie respectively. Now, up until this point, if we would have committed the both transaction tree or the combined transaction tree to the ledger, the balance distribution between all 3 parties would have been the same. We have not yet performed any state transition or any payment. However, now in this case, we have a temporary channel between Alice and Charlie, as well as the punished transaction. We can now perform a payment by, instead of giving the coins within the merge transaction to Alice, we now give them to Charlie. Here we have performed a payment. Now, the last step will be that we want to consolidate the payment and go back to the initial state where we just had 2 individual channels, one between Alice and Bob, one between Bob and Charlie, but with the modified balance distribution. So while doing this, we again do not want to perform any state update in a way that we would perform a payment between the parties. So the first step is we use Bob as an intermediary to atomically again create 2 new transactions that spend the split transactions outputs, but now give the coins to Bob and Charlie respectively. Lastly, since we have now 2 separate transaction trees again, one that is exclusively controlled by Alice and Bob and one that is exclusively controlled by Bob and Charlie, both pairs of parties can perform one last transaction tree update to reopen the channels on top of the UTXOs that are on the ledger, but now with the updated balance distribution. Effectively, we performed a payment from Alice to Charlie. Our construction is designed such that it can be extended to arbitrary many hops. First, here, we create a temporary channel between Alice and Charlie, as well as one between Charlie and Eve, in the same manner as we showed before. However, we can reuse these temporary channels to create a direct channel between Alice and Eve. This channel can now be used for a direct payment between Alice and Eve. Next, we perform this consolidation step with Charlie as intermediary in this case to apply the payments on the temporary channels on the level below. Lastly, we can repeat the step now with Bob as intermediary and Dave as intermediary to apply all payments to consolidate them on the original payment channels. Now, when evaluating our approach, we show that although the log time for an individual party, the worst case log time is logarithmic in the payment path length. This would be the case for the party that acts as intermediary on the very top of the construction of the payment tree. Because of the balanced binary tree structure of the construction, the sum of all collaterals, the total collateral, is only linear in the length of the payment path. This is comparable to sprites, and by a factor of n, lower than the total collateral of HTLCs. However, in contrast to sprites, we do not require any smart contracts. As a trade-off, the number of transactions that would need to be committed to a ledger in case of a dispute. In the worst case, it's an logarithmic amount of transactions by any party, meaning again, by sender and receiver of the payment, as well as the intermediary on the top of the construction. However, again, if we look at it macroscopically on the transaction as a whole, the number of transactions committed to the ledger is linear to the length of the payment path, which is, again, the same as with HTLCs and sprites. Thank you for your attention.